Every day, the world's merchant fleet moves about 27 million tons of a cargo that nobody buys, nobody sells, and nobody is paid to carry. It's seawater. Ships pump it into tanks inside the hull before sailing, and pump it back out at the other end. And over a year, it adds up to something in the order of 10 billion tons shifted between the world's ports, enough to fill roughly 4 million Olympic swimming pools. It isn't waste, and it isn't a mistake. Without it, a large number of those ships could not safely cross an ocean at all. But seawater is not an inert substance. It is full of eggs, larvae, plankton, spores, juvenile fish, and the International Maritime Organization estimates that at any given time, more than 7,000 different species are riding inside ballast tanks somewhere in the world, being carried from the sea where they belong to one where they don't. In 1982, one of them arrived in the Black Sea. 10 years later, the region's anchovy catch had fallen from 200,000 tons a year to 200. So what goes so badly wrong when a ship sails empty that this is the fix? A ship is designed to float at a particular depth. Naval architects call it the draft, the distance from the waterline down to the bottom of the hull, and every calculation about how a vessel behaves at sea assumes it. The hull shape, the position of the propeller, the height of the bridge, the stability figures that determine how far she can roll before she stops coming back. All of it is worked out for a ship sitting at her design depth, with cargo aboard. Take the cargo out and she rises. And a ship riding high is not a lighter version of the same ship. It's a different machine, and a worse one. 3 things go wrong at once. The propeller comes up toward the surface. It's designed to work fully submerged, in solid water, and as it rises it starts to draw air down from above. The blades cavitate, the thrust falls away, and in a swell the propeller can break the surface entirely, hammering the shaft and the engine with loads they were never meant to take. The rudder rises with it for the same reason and with the same result. Steering depends on water flowing across a submerged blade. Lift it toward the surface and the ship's response gets vague at exactly the moment she needs it most, because the third problem is the wind. An empty hull sits high out of the water, and the exposed side of a large ship is an enormous flat surface. A container vessel with empty holds is a steel wall several hundred meters long, presenting itself to the weather. Crosswinds push it sideways. In a gale, it becomes a sail the crew cannot reef. Driven downwind, with a propeller half out of the water and a rudder that has lost its grip. And underneath all three sits a subtler problem. A ship's stability comes from the relationship between the shape of the submerged hull and where the weight sits inside it, a balance the naval architects calculated for a loaded vessel. Empty that vessel and the balance moves outside the range it was designed for. She can become tender, rolling further and returning more slowly. Add too much weight too low, and the opposite happens. She becomes stiff, snapping upright so violently that cargo breaks loose and crew get hurt. Ballast isn't just weight, it's weight in a calculated amount, in specific tanks, to put the ship back where its designers assumed it would be. For centuries, the answer was solid. Stones, sand, gravel, iron. It worked, and it was miserable. Ballast had to be loaded by hand, shoveled out by hand, and stored somewhere ashore between voyages. Ports built whole industries around it. Then someone worked out that the ship is already floating in millions of tons of a free, heavy, self-delivering ballast material, and that all you need to move it is a pump. Seawater is perfect. It costs nothing. It's available at every port on Earth, in unlimited quantity. It flows in and out in hours rather than days, needs no storage ashore, and sits exactly where you want it, in tanks along the bottom and sides of the hull. There is only one flaw in it, and it took decades to notice. The flaw is in the timing of the two operations. A ship takes ballast on where it has just unloaded and discharges it where it is about to load. That is the whole point. The water replaces the cargo's weight, then gets out of the way when the cargo returns. But it means the tanks are filled at one end of a trade route and emptied at the other. A bulk carrier drops coal in Japan, fills its tanks with Tokyo Bay, sails to Australia, and empties Tokyo Bay into the harbor at Newcastle before loading the next cargo. A container ship pumps out Shanghai and Los Angeles. And what goes into those tanks is whatever is floating in the harbor on the day. Not just water, but everything suspended in it. Which is a great deal. Coastal and estuarine waters are where a vast share of marine life spawns, and most of what lives there begins microscopic. Eggs, larvae, spores, cysts, juvenile fish small enough to pass through an intake screen. A single tank can hold tens of thousands of tons, drawn from precisely the water where those species breed. Most of them die on the voyage. The tank is dark, the temperature and salinity shift, the food runs out, and a 2-week ocean crossing kills the overwhelming majority of what came aboard. The survivors are the entire story. because a species that can endure weeks in a steel tank with no light and no food is, almost by definition, a hardy generalist. And a hardy generalist arriving in a new ecosystem with few of its usual predators is the precise recipe for an invasion. Which brings us back to the Black Sea. In 1982, a ship loaded ballast somewhere on the American Atlantic coast and discharged it in the Black Sea. In that water was a comb jelly called Menemiopsis lygi, a translucent, walnut-sized animal, native from New England down to Argentina, where it lives at unremarkable densities because plenty of things eat it. It arrived into a sea that was already in trouble. Decades of fertilizer running off the Danube had loaded the Black Sea with nutrients, and its large predators had been fished down hard. The defenses that would normally hold a newcomer in check had been dismantled before the newcomer showed up. For 6 years, almost nobody noticed. The animal was misidentified at first, and not until 1989 did anyone establish what it actually was. By then it had done something extraordinary, reaching densities above 500 individuals per cubic meter and an estimated total biomass approaching 1 billion tons of wet weight in a single sea. Menemiopsis eats zooplankton. It also eats fish eggs and fish larvae. In the Black Sea it ate all three, at that density, across the entire basin, consuming the anchovies' food supply and the anchovies themselves before they hatched. The anchovy catch went from 204,000 tons in 1984 to 200 tons in 1993. Sprat halved. Horse mackerel went from 4,000 tons to 0. Total Black Sea fisheries yield fell from around 750,000 tons in the 1980s to 200,000 by 1989. Turkey, Bulgaria, Ukraine, Romania, Georgia, and Russia all fished that sea. All of them lost the same fishery in the same decade to an animal that arrived as an invisible passenger in a tank of water somebody needed for stability. Proving the connection took years. A species turns up in a harbor. The ship that carried it sailed long before. Nothing was declared, weighed, or inspected. In the Black Sea, it took 7 years just to correctly identify the animal that was eating the fishery. But by the 1990s, the pattern had repeated in enough harbors to be undeniable, and the International Maritime Organization began drafting rules. The first answer was beautifully cheap. Leave the water untreated and change where you dump it. That became the D1 standard. Ballast water exchange. Mid-ocean, at least 200 nautical miles from land and over water 200 meters deep, the crew pumps out the coastal water they loaded and replaces it with deep ocean water. The logic is elegant. Estuarine organisms mostly cannot survive in the open ocean, and open ocean organisms mostly cannot survive inshore. Swap the cargo of life in the middle, and whatever you eventually discharge in port arrives already unable to live there. It costs almost nothing. It needs no equipment. And it half works. You cannot flush a tank completely. The standard asks for 95% volumetric exchange, which leaves a residue, and sediment on the tank bottom holds cysts and eggs that pumping doesn't lift. Worse, the operation itself carries risk. Filling and emptying tanks in open ocean puts stresses on a hull at precisely the moment it's exposed to weather, and there are conditions where a master simply should not attempt it. D1 was always a stopgap. The real answer is D2, and it changed the question entirely. D1 asked whether you performed a procedure. D2 asks what is actually alive in the water leaving your ship. The limits are specific. Fewer than 10 viable organisms per cubic meter for anything 50 micrometers or larger. Fewer than 10 per milliliter for the size class below, and hard ceilings on cholera, E. coli, and enterococci. Meeting that requires machinery. And after entering force in 2017, the convention set a final deadline of the 8th of September 2024. Every ship covered by it now needs a treatment plant. Most work in 2 stages. First, filtration, a mechanical screen straining out larger organisms and sediment as water comes aboard. Then the treatment stage, where the industry split into 2 camps. Ultraviolet systems pass the water through banks of UV lamps, damaging the DNA of what survived the filter. The organisms are not killed outright. They are rendered incapable of reproducing, and that damage takes time to become final. Which is why UV works in combination with the water simply sitting in the tank afterwards, for days, before discharge. Electrochlorination takes a different route, running a current through the seawater itself to generate chlorine in place, dosing it into the flow and then neutralizing it before discharge. Because chlorine leaving the ship is regulated in its own right, and a system dosing too heavily fails inspection just as surely as one dosing too lightly. UV is simpler and cleaner. Electrochlorination handles the enormous flow rates of large tankers, above 1,000 cubic meters an hour, where UV becomes impractical. The cost is substantial. Building it into a new ship adds somewhere between $500,000 and $2 million. Retrofitting an existing vessel is worse, because engine rooms were never designed to accommodate a filtration skid, a UV reactor, and a cabinet of lamp drives. The installation alone can run from $250,000 to $800,000 before the equipment itself, and roughly 30% of ships still fail their biological inspection. 30% is a strange number, because a failed inspection doesn't necessarily mean broken machinery. Some of it is maintenance, fouled quartz sleeves, aging UV lamps, worn electrodes, filters clogged by turbid harbor water. But some of it is subtler than that. A UV system pushing through murky water needs longer exposure to deliver a lethal dose, which means the crew has to slow the ballasting rate, run the pumps at full speed to save time on a tight port call, and the machinery performs exactly as designed while delivering a dose that doesn't work. The ship gets sampled and fails, with a functional system humming away below decks. Installing a solution and operating one are not the same thing, across tens of thousands of vessels and the crews who have to run them, which fits the history of this problem, because ballast water has produced unintended consequences at every stage. Somebody solved a genuine engineering problem, how to make an empty ship behave like a loaded one, with the most obvious material available. It was free, it was everywhere, and for decades nobody had reason to look closely at what was in it. The solution worked perfectly, and it also turned shipping lanes into corridors for living things. The Great Lakes were reached through the St. Lawrence Seaway, the Black Sea from the American Atlantic, the Caspian from the Black Sea. The routes that carry cargo carry everything else too. The convention has made a real difference, but it is an attempt to sterilize a symptom, because the underlying fact hasn't changed. As long as goods move between continents, ships will move ballast between ecosystems. The industry has spent billions learning to filter what it carries, and it will go on carrying it. There's a coda to the Black Sea that nobody planned. In 1997, a second comb jelly arrived, probably in ballast water, like the first. This one, Baro ovata, eats Menemiopsis. Within 2 years, it had spread across the sea and driven the invaders' population down, and the fisheries began to recover, helped along by a collapse in the fertilizer runoff that had been feeding the whole system. The two jellies have oscillated ever since. Nobody arranged any of that either. Something is being pumped into a tank somewhere right now. In a fortnight, it'll be somewhere else entirely.